So 11,000 liters, this means something to all of us. This is a magic number, right? It's the amount of air we breathe every single day. It's a significant amount of air we breathe. And the funny thing is, we care so much about exercise, we care about eating healthy, we do so much to stay healthy, but we rarely influence the quality of air that we breathe. And this is really a strange thing because it has a hidden cost. There is an underlying hidden cost that has both health implications, but also energy implications and massive energy implications. So just imagine one scenario. Would you put yourself inside a glass jar for about 8 hours a day, roughly? I don't think anyone would reasonably think this is a good idea. But we do that. We do it in a very strange way. And more importantly, we want to keep this glass jar at an optimal temperature of about 20, 22 degrees. We want to keep the CO2 levels at an optimal level so that we don't get too tired or drowsy. So where are these glass jars? They're all around us. Everywhere you look at New York, you look at London, and now Bangalore is aping exactly the same model. And this July, I was out on vacation, went to visit my in-laws in Coimbatore, and I was a bit shocked to see more glass jars showing up in a small town in India. It was really paradoxical, right? And so how do we keep this exact temperature and exact air quality inside the glass jars? You might ask yourself. There's two things we do fundamentally. We either cool or heat the space, depending on which part of the world you are in, what's the geography. And more importantly, you move the air inside these jars. So you circulate the air, you pick out air from the outside, you recirculate it inside, and you push it out so that you keep the air quality within reasonable conditions. And so sometimes in that process, you also filter the air because in some parts of the world, the air quality outside is really poor. And this has a profound impact because the operational cost of running these glass jar buildings up and running is roughly 3 times the embodied carbon that's used to build them. And that is if it's new built. If you compare it for older buildings that were built, say, 5 years ago, 10 years ago, it's sometimes as much as 10x. And it's really, really a big challenge. It's become so big an issue that this glass jar has become so heavy now that it's outcompeting the airline transport industry in terms of carbon impact. So the big question is, what is our basements hiding? Have any of you gone and looked at any of your basements anytime in the recent past? Very unlikely, but that's where the crux of the whole problem is, really. So I've been on this 10-year obsession, sort of, to decipher this issue, this kind of Rubik cube that I keep playing with, and trying to figure out what is it that we can do, really, to change this. And I've come to a very basic conclusion after a lot of reading tons of reports, analysis, whatever, trying different experiments, trying different projects with all kinds of customers, dozens and dozens of projects. And there's fundamentally 3 things we can do. We can design our buildings better. We can use better materials, better processes, better technology. You can be adaptive, which is a good thing to do, but still it's a Herculean task because you're trying to shift the paradigm in the industry. You're trying to convince someone to not do things the way they do things today. And that's really hard. The other thing you can do is you can optimize your existing buildings, which is a reasonable shot, and I'll tell you a little bit more about that. The last thing you can do is nudge our behavior and our expectations of us as people. Can we do something directly? So I just want to show you 3 examples. So the first one about building with better approaches, materials, and technologies. This is a case that I picked from one of our very close partners, Velux Group, which is a big Danish company that makes roof window systems and very, very sophisticated, high-quality building materials technologies. They had proven recently through a project called Living Places that using natural ventilation, timber construction, and all kinds of carbon-neutral techniques, they could produce living spaces, standard Danish family houses, for less than 3.5 kilos of CO2 per square meter, which is roughly 1/3 the typical average that happens today. And we were very, very happy to be part of this thing because in terms of the environment inside also, in terms of daylight and thermal quality, comfort, air quality, we were able to quantify all of this stuff and prove that these buildings are top-notch and they're not any different than all those glass jars that you tend to bin. And these kinds of techniques do exist in our everyday life. In India, we've been having these elements of vernacular architecture forever, since time immemorial. The basic things like creating ventilation through jalis, they create the venturi effect or the chimney stack effects. We had evaporative cooling methods. We learned how to bake the right types of materials and the right thickness of the walls in order to create the right thermal mass. Balki spoke about long-term storage. These things exactly do that, or used to do that. If you go to any of our really ancient architecture, they had massive amount of energy storage built into them. Then comes the other question. There is huge amounts of existing buildings, and we cannot tear them down just to build new buildings all the time. Especially in many other parts of the world, this is very, very relevant because there's a lot of heritage buildings and older buildings that need to be preserved. So we have to also figure out a way to optimize our existing buildings. So this is a case that we did in Copenhagen, which is a really fascinating office building where we managed to slash down the energy consumption of this building by nearly 50% with a payback period of about 2.5 years. This means the investment almost pays back itself instantly, and it creates massive value downstream for the next, 50, 70 years of its operational life of the equipment in the space. And how did we do that? So we have developed a pretty nifty little sensor technology that actually goes into the buildings. It typically is mounted on the roof or on the wall, and it measures a whole bunch of things. That includes occupancy, it measures the carbon dioxide levels, a dozen different parameters. And we use this data in 3 layers. So the fundamental data is that we capture data on the indoor climate. So we capture all the parameters possible. We analyze the noise. We can tell what kind of activity there might be happening there. We can understand the solar loads coming in from the outside, the rate of people coming and going into the space. Then we couple that with energy price forecasts. We couple that with weather forecasts, occupancy forecasts, and then we build a building optimization model in the classical AI sense that we then use to control the actual air supply, heating, and cooling in the building. And this is a simple retrofit solution that we co-developed with a large Swedish conglomerate called the Lindab Group, who was very, very active in mechanical ventilation systems. And the best part is the system is a pure retrofit. This is the closest you can get to changing a light bulb in a technical system like ventilation systems in buildings. And it's fairly easy to install. It takes literally an hour. You have to insert this into the ducts, install the sensors, everything is wireless, it self-configures, it connects to the cloud and starts learning. And it starts learning your behavior, the room's conditions over time, and that's where the magic really happens, because we want to prove this with a data-driven paradigm. So of course we capture a baseline on how much energy is being consumed, and then we use the algorithms to start optimizing the building, and when the true learning happens, you can start seeing 50, 60, 70% in savings sometimes. Then I want to just touch upon the most difficult of all of these things, is changing human behavior. And this is actually my favorite thing that I think my team and I have put together over the years. So we developed a product in collaboration with the Danish architecture firm called 3XN, GXN, and with the Velux Group. It's a little bird. I'm sure you heard of canary in the coal mine. So it's a little bird, and it does one thing really well. It keeps track of your indoor climate and chirps like a bird when it's time for you to naturally ventilate your space. And this saves mountains of costs for the building in terms of infrastructure, and it makes it a fun thing. It engages kids, it engages entire families, it builds new types of behavior in your life. And this was a really successful thing in schools especially. And schools always have really terrible conditions. You cram 20, 30, 40 sometimes kids into a classroom and with one teacher, and you have expectations of high learning ability, and the cognitive capabilities are really tight in these spaces. So we really nudge behavior with this. And the best part is we've designed a little package that goes for schools. This is an open source kit that goes to educate classrooms on how to keep their environment better and cleaner. So there's a constellation of 3 things coming together. There's huge amounts of data, there's a lot of sensors, there's AI principles, and all of this can be actually harnessed to do something significantly important to change the paradigm of how much energy and carbon impact we have through our buildings. This goes back to prove one thing: we need to pay more attention. But the technologies and the solutions to solve these things are available. So the big question is, how do we get that going? Thank you so much.